Hey, good morning, everybody. Welcome to another lesson on Papa Lim Physics Classroom. Okay, on my physics channel, I will be uploading videos regarding to the topics I taught in class and the test or the tutorial questions that we're going through. Okay, if you think this content or these materials are relevant to you, remember to subscribe to my YouTube channel and turn on the notification bell button so that whenever I upload these materials, you can actually get notified and you can actually review them ASAP. And if you have questions, you can actually leave a comment, leave your comments or leave your emails at the bottom, or you can email me your questions so that I can actually get back to you ASAP. Okay, for today's lessons, okay, we will be looking at chapter 4 in the science physics section, which is dealing with mass, weight, and density. Okay, it'll be broken down into 3 different sections. Okay, the first section we'll deal with is your mass, weight, and weight. Okay, so the second section will be inertia, followed by 4.3, which is density. As of now, we look at mass and weight first. Okay, mass and weight is quite a common, is a very common term that we actually use interchangeably in our real life. Okay, but actually, fundamentally, if you look at it, the mass and weight. Okay, if you ask an English teacher, you find that they actually refer to these two terms as interchangeable. But in terms of science, they are actually uh, two different, two different concepts. Okay, for mass, it's actually looking at the amount of matter that's in the body, the amount of molecules that's in the bodies. Okay, it's literally down to each individual moles of molecules. Okay, and the unit, SI unit that we use for mass when we calculate it in terms of kg. Okay, so let's say if I ask my mom, okay, what is the mass of the body here? She will definitely look at me at like with a very strange ideas, strange look, whereby I say, why talking about why is it mass? Is it weight? Okay, because in real life we actually use weight very often, and when we say weight in real life, we actually refer to mass, which is in kg. But actually, fundamentally, weight is actually a gravitational force. It's actually a force. Okay, it's a measure of the force, the force acting on it. Okay, and the SI unit is actually Newton. Weight is the outcome. I would say weight is a vector or is the outcome when mass and gravity actually interact with each other. And the outcome of that is what we call weight. Okay, so fundamentally, they refer to, I would say they are referring to the same things, like how heavy I am. But when we say heavy, the correct term that we are referring to is actually the mass, okay, the amount of molecules I have in the body. Weight has the idea of the body itself, the mass of the body, making reference to the gravity pull of the planet. So together, these two factors will actually combine to give you the term known as weight. So if you look at weight actually you exist in the area whereby you have actually gravitational field. Okay, gravitational field strength, whereby you exist in the area whereby you feel the gravity pull. That area, that field is what we known as gravitational field. Okay, it's the area or is the region whereby actually a mass and object actually feel a force, okay, due to the gravitational attraction or what we call the gravitational pull. Okay, or sometimes we loosely call it gravity. Okay, so whenever a mass is placed in the gravitational field, the pull, he will actually experience the pull. The pull is termed as gravitational force. And this force, we have a name for it, and it's called the weight. So the mass of the object coupled with the pull of the planet, that field or that term is what we call gravitation, is what we term as gravitational force, or aka weight. So weight has two components inside, which is the mass and the gravitational field strength. And gravitational field, okay, is the area you'll find that the strength of this field, the gravitational field strength, okay, is strongest at the surface of the liquid, and it's get surface of the earth. Okay, whereby the gravitational pull loosely defined is like 10 Newton per kg, whereby I'm pulling you, the gravitational pull is actually strongest at the surface. And as I get weaker, it get weaker. As I get further away, it get weaker. So as I am further away from the surface of the earth, my gravitational pull actually decreases. Eventually, when I go out to space, like far away from earth, you'll find that my gravitational field strength actually will drop all the way down to zero. Okay, and that's what we call in space, or what we call, you have this experience called weightlessness. Okay, now same thing, if you reverse it, you'll find that it actually gets stronger okay, as the object moves closer to the Earth. So if I am going down to the Earth, okay, that's why when we're going to get a drill and drill all the way to the center of the Earth, you'll find that as I drill nearer to Earth, the pull of what I call the gravitational field strength is actually increasing. Okay, so if I'm going deep down into the surface, you'll find that the gravitational pull, the gravitational field strength is actually stronger than what it is at the surface. Okay, so that's why if I dig all the way down to the core of the Earth, the center of the Earth, which is like thousands of kilometers away, you'll find that the gravitational pull, okay, is actually much, much stronger than compared to it is at the surface. Okay, now gravitational field strength is the pull. Okay, loosely defined as the pull. Okay, is defined as gravitational field force per unit mass. Okay, loosely we will look at it as the gravitational pull. Okay, the pull, it has a number at surface. The strength of it is actually what we call 10 Newton per kg. So with this, you will know that, okay, for every 1 kg, the force acting on it is actually 10 Newton. Okay, so this is what we mean by gravitational field strength. Okay, and the number is 10 Newton per kg. Okay, now when you look at it, okay, if you compare weight and mass side by side, like what I've done here, you'll find that there's actually a subtle difference between them. They are looking at two things. Mass, okay, is the object itself. Let's say this is the object. Okay, but for weight, remember when you look at the weight of the object, yes, I'm still looking at the object itself, but I need to I need to couple in with the field strength, okay, of the planet, or sometimes we call this the pull of the planet. Okay, so together, the object and the field strength is actually what we known as the weight. So, and weight is a force, which is in Newton. Okay, and mass, which is the amount of matter, is talking about the number of molecules I have. Okay, and how heavy each molecule is, and when I sum up all the molecules, is actually what we known as the mass of the object, which is in kg. And like you all know, Newton's forces, all these are vectors. So mass is scalar. There's no sense of direction. 20 kg, 20 kg doesn't mean anything in terms of directions. It just tell me how heavy I am. But it never really tell me how heavy I am in a particular direction. Okay, no. Okay, same thing. Mass is independent of field strength, definitely. Okay, regardless, it depends on the amount of matter I have. So regardless of what planet I have, as long as I am there physically as the same body, the amount of matter I have in my body when I'm in planet Earth and when I'm in planet Jupiter, the amount of matter is always the same. So that's why mass actually remains constant when I go from different planets. But weight actually depends on gravitational field strength, which means the different planet with different gravity field strength, different gravity pull, my weight will actually be different. And I actually have a formula for it. Okay, weight, okay, the formula for it is mg. Okay, mass of the object, g is the gravitational pull of the planet. And for example, Earth, okay, the gravitational pull is 10 Newton per kg. In some book, you'll find that the gravitational field strength is actually 9.81 Newton per kg. Okay, so this is the much accurate version. But for upper sec 3 and sec 4, or what we call the year 9, year 10, okay, you'll find that the gravitational field strength, we actually round it off to a whole number for simplicity, for calculation, ease of calculations. So 9.81, we actually round it off to a whole number for 10 Newton per kg. And W is the weight of the object, and the unit is Newton. One thing to take note is when you look at the formula, when you want weight to be the SI unit Newton, which is the only unit, please make sure that the mass factor in all the factors, the mass, the gravitational field strength, the gravity pull is in SI unit. For example, mass must be in kg. Okay, then for gravitational pull, it has to be Newton per kg. So the SI unit you have to obey because the final answer you're looking for is also in SI unit. So every terms in the formula must be in SI unit. Okay, so once you are okay with it, I will not say it's complicated, just need to do a mental differentiation between mass and weight. So there is actually fundamentally a difference. So when I have actually mass 1 kg on planet Earth, in the same box is moved to planet Moon, and on the same box is also moved to the space, you'll find that the object actually has one particular relationship, whereby the mass is always 1 kg, like what you see here. Okay. But the weight of the object, this is mass, but the weight of the object, it actually depends on the formula mg. Okay, the weight of the mg, it takes m is 1 kg, gravitational pull of Earth, if you look at the moon, the weight of the object on moon depends on the mass of the object plus the gravitational pull of the moon itself. Same thing for the 1 kg mass, the weight of the object in space depends on the mass of the object, which is 1 kg plus the gravitational field strength of it in space. Okay, so you take note, you will see that on Earth, okay, let's say if I say my G is 9.81, so you'll find that 1 times 9.81, let me use another color. Okay, you'll find that if I use G as 9.81, okay, so 1 times 9.81, you'll find that the final mass will be the weight of the object, okay, weight, which is Newton, is 9.8 Newton. On the other hand, for the same object, if I bring it to moon, gravitational field strength is actually 1.6 Newton per kg. So together, the 1 kg object actually now weighs 1.6 Newton. Okay. On the other hand, if I have the same box again, I shift it all the way to space. Okay, 1 kg mass, I'll shift it all the way to space. What's so peculiar about space is that in space, my gravitational field strength, my gravity pull is actually 0. Okay, and because of the formula, and because of that, my gravitational field strength is 0, you'll find that I actually have 0 Newton, 0 weight, but 1 kg mass. Okay, it is still possible. That's the 1 kg, the 0 Newton is what astronauts or what people in space always term it as weightlessness. I actually don't feel my weight. Okay, it's not that I don't feel my mass. I still have my mass, but I don't feel my weight because my weight depends on mass itself and the planet and the gravitational pull of the planet. And if my planet, there's no planet nearby, my gravitational pull is 0, my weight will actually be 0. Okay, so all in all, okay, just take note, there's a fundamental distinction between mass versus weight. Okay, and it is possible, and before that is the formula of weight, which is weight equal to mg. And the last one you have to remember is it is actually very possible to have a mass of a certain number. But yet at the same time, it's possible for the same object to have a weight that is equal to 0 Newton. It is very, very possible because the gravitational field strength of the planet is actually 0, aka space. Okay, so if you are still not sure about, or you want to take note of the distinction between mass and weight, okay, you can pause the video and actually rewind back 2 or 3 minutes to look at the differences of the formula between mass and weight. Okay, so with that, I've come to the end of this particular section for this particular section 4.1. Okay, if you have any questions, feel free to drop me a comment or drop me an email drop me an email so that I can actually get back to you. Okay, if not, okay, just stay tuned for my next video on 4.2 inertia. Okay, and same thing if you want to know, if you want to be informed of when I uploaded the video, okay, remember to subscribe to my channel and turn on the notification bell. Okay, with that, okay, that's all, folks. Okay, see you next time. Bye bye.